All right, so I think as my colleagues have been pointing out in a way during the first half of the tutorial, creating the proper and appropriate platform for this joint computation and communication has to go through this multi-tier computing in a way. You have the joint communication and computation. You have we started from a single cloud to multiple clouds and eventually to a hybrid cloud slash mobile edge computing. So especially in the previous application, we've been coming across this important rate splitting strategy. So just going across the same lines, next in line, I'm gonna be going over an important aspect of also the cooperation in terms of this multi-tier computing, especially with an actual application related to extended reality. So of course, extended reality nowadays, including VR, including AR, are of course growing at a fast pace, and so it's important also to manage their actual operation. XR devices, whether we're speaking about some headset or maybe some iWatches or other type of maybe head-mounted sort of devices, they need their own management, and so we're gonna be illustrating this in the sequel. So that's the next discussion. So the idea here is the fact that extended reality application nowadays are going viral, and we're gonna show how this sort of hybrid cloud mobile edge computing will help a lot. But also we're gonna show that the idea of coordinated or cooperative non-orthogonal multiple access becomes especially important when we are dealing with two type of XR devices, a strong and the weak in the weak device, because not all devices will have a strong line of sight or a strong sort of connectivity to the main server or the main serving point. So it becomes quite important to utilize this cooperative normal scheme, as I'm going to be illustrating next. Right, so we have also all been working on this extensively ourselves, among other esteemed researchers. And here, if I were to single out a single, in a way, reference for interested readers, I would actually single out for our recent paper that just appeared in April 24th, in April, just last April, April 2024, on the topic. It actually now is in the IEEE Internet of Things journal. Again, it's also co-authored with my colleagues Robert Reifert and Aiden. All right, so what's the idea here? The idea, of course, is now we are showing a huge popularity in XR devices. Of course, a lot of competitors nowadays are coming up with their own head-mounted devices, whether it's an actual simple wearable device or an actual headset, an actual sort of glass, which makes good use of augmented reality type of applications. The idea, of course, is you need eventually to have some sort of video that have to be encoded, pre-rendered, modeled, and eventually has to be transmitted to a certain serving point. The serving point eventually have to serve the actual device. So this is the idea, and of course you could have this either on an actual very strong cloud, or maybe it's actually it's at the edge, and you would need a certain computing or mobile edge computer to take care of such operation. Such an example procedure could be when we have a head-mounted display receiving a 360 degree video stream, and of course you have to model and render the environment, which eventually has to be done at the strong processor, and eventually you're going to be getting some control input, particularly from the head-mounted device, such as movement, data, the FOV, the field of view, and so on and so forth. All right, so this is the idea, but also at the same time, as I mentioned, not all devices are strong enough. So you could have some strong device that's strong, for example, the head-mounted display, but maybe the watch, the smartwatch, is not strong enough, or doesn't have an actual strong connectivity or strong channel towards the serving unit. That's why you need eventually to have to come up with a certain relaying capabilities that help out with the service of such an extended reality device whenever the channel is not available. So before going into the cooperative NOMA perspective, of course, classically in the literature, you could always come across a lot of cooperation and interference mitigation and management schemes. For example, the cooperative relaying, which is in fact particularly fit for combating the channel impairments whenever you have some fading, some path loss, some shadowing, especially for the sake of extending the coverage range, the coverage coverage radius. Of course, you could in the literature there's a lot of protocols for relaying, such amplify and forward, decay and forward. Another multiple access scheme, which also has attracted a lot of attention, is that one related to non-orthogonal multiple access. The idea here is you have multiple users using the same time frequency resource block, and eventually you can utilize some of those successive interference cancellation to make sure that both users are jointly being served. Recently, there has been this increasing interest in what we call co-NOMA or cooperative NOMA. And the idea is that whenever there's a weak user that cannot be served by the serving node, it could actually rather be served by the by an actual stronger user. So assuming you have two users, U1 and U2, U2 cannot be served directly by the source, so eventually it could perhaps be served by the strong user instead. Right, so that's from a general cooperative multiple access perspective. In our own context, and going back to the context of extended reality users or XR users, you could have eventually a lot of users spread out across the network, and they could be denoting a certain head-mounted display and maybe another smartwatch. One of them is strong, one of them is weak, in a sense that one of them may have an excellent channel to the serving node, the other one would have not that really good channel, and so we will have a strong and a weak user in the process. And of course the idea here is you have again an actual hybrid cloud or central cloud network, which we also call the cloud tier, which is coexisting with edge tier, which is the UAV, the mobile edge computing tier, truly, right? So you have eventually have a distinct set of radio access network resources. You will have both type of users or devices, strong device and weak device, and the idea would be to determine what are the beamforming vectors that one has to be utilizing towards the strong and the weak users, but also we need to know whether the weak user is going to be utilizing the relay link or it's going to be served directly by the serving node, whether it is an actual mobile edge computer or a UAV in this case, or an actual base station that's connected to a cloud or to the central cloud and using this particular node, right? So the problem here would be about how can we make good use of this hybrid central cloud and mobile edge computer to try to serve the extended reality well. Of course, there's a lot of important features or important metrics to account for, as we're going to be seeing. Of course, one of them is the actual computational metric, which is related to the number of computation cycles and number of computation per cycle, and also the delay. Of course, there's a different type of delay whenever one user is served by either the mobile edge computer or the base station, right? So that's truly the idea. You have basically the presence of cloud UAV and intra-cloud interference, so different modes of interference. How can we mitigate the intra-cloud, or what you call also the intra and also the intra-edge computers in a way, interference via SDMA, and of course here we have to at the same time utilize the device cooperation. When I'm saying device cooperation, that means we have to make good use of the good channel between the XR devices in case the channel between the weak user and the serving node is not good enough. All right, so this is the idea. That's what we're going to be discussing here. So what we are taking into consideration is a coexisting central cloud and mobile edge computers. We have different type of users. We have both strong and weak users. The strong users are denoted by, in a way, the purple color. The weak users are the one in pink. And eventually we have predetermined user association. That is, we know which one is strong, We know which one are weak based on the channel information. And we would like now to know what is the beamforming vectors, that is, what is the beamforming vectors of the strong users, and what's the beamforming of the weak user, given that the weak user could be either be served by the strong user by relaying, or it could be served directly by the actual transmitting node, right? That's the idea. Of course, we need also to determine the transmit power, and we need also to determine what are the rates of the strong and weak users across such a complex network. Again, this paper recently has appeared in IEEE journal of IEEE Internet of Things journal. We solved a complex problem by accounting for a lot of constraints. Some of the constraints we accounted for, of course, was a power constraint. We have two type of metrics, or two type of consumed power metrics. We have the power consumed by the base station of course being served by the central cloud, and we have also the power consumed by the edge computer, which is truly the UAV in this particular case. So that's why we have two definitions for the power. Whenever we have a power consumed by the base station, this will be a function of both of basically the simple in a way communication type of transmit power, the classical transmit power communication, but especially for the edge computer consumed power, we have other type of consumed power at the same time. One of them is related to the computational power, which is denoted here by this particular value, which is inside the red box. And also you have an additional amount of power, which is basically the power that is related to the mechanical and operational aspects of the UAV or the mobile edge computer in this case, in this situation, right? So the question would be, how are we going to be balancing and striking a good trade-off between matching the good communication metrics we opt to get, and also in a way manage the computational resources given the fact that we have some computationally limited type of mobile edge computer. All right, so this is the idea. Of course, as we said, this is a first important aspect. The other important aspect is as well the overall user delay. So basically, there's each user, whether it's a strong or a weak user, will be subject to some particular delays. These delays are in fact of three different types. Either if they are the computational delay, and of course the computational delay is here related to the process to the user task, to each user task, and how long does it take to compute its own task. And this is basically the one here, which is inside in a way the pink box. And then you have the one inside the purple box. That's truly the front delay. So you compute the task of each user, then you need to transmit it over the front haul link, and of course here you're going to be paying for some particular delay. And of course at the end you will have the transmission delay, which is a delay related to every particular user. These are the in a way the delay. The transmission delay is the delay which is quite close to what particular data each user wants, what particular size of the data each user is asking for. All right, so that's the idea. Eventually, the problem that we focus on is about maximizing the sum log rate, which is an excellent objective function when one is trying to get into some sort of fairness. The sum log rate has been shown to act very well, especially from a fairness perspective. Of course, that's especially important in this particular aspect of XR devices, because we are acting upon two different type of devices, strong and weak, and we're trying to balance their own data rates. And of course, what are we taking into consideration? We're taking the computational capacity into consideration. We're taking also we try to select whether the user is going to be, whether the weak user is going to be served by its strong sort of separate pair or from the actual serving node. We also have some achievable rate constraints, of course, to make sure that we are still acting, or we're still belonging to the achievable rate region. We have the front haul capacity of every front haul, and we have the power consumption, which we spoke about. And of course, we still have the delay constraints per user, which is a very important metric, especially given the latency sensitivity of XR devices. So delay constraints per user would become a super extreme type of constraints in this case. All right. So that's a problem we actually solved. It's a mixed discrete continuous optimization problem, which is quite complex to solve. Finding the global optimal solution of such problem is likely of exponential complexity. So we opt out for some practical practically feasible type of numerical solutions. And the idea here is to utilize the heuristic L1 norm approximation to deal with the binary constraints. We also utilize a successive convex approximation to linearize the non-convex constraints and eventually render the problem in a way that in the inside loop as an actual convex optimization problem. We also look into what we call the worst case delay approximation also to render the problem numerically feasible. And last but not least, we also utilize the problem eventually ended up being akin to an actual fractional programming, and we have utilized some of those recent results in quadratic transform to solve the problem in its way. By iteratively sort of solving this problem based on every particular node, we were able to get a distributed implementation to such algorithm, which is of course going to be also highlighted shortly numerically. But the idea is that when you are able to solve the problem on a per node basis and eventually interchange some information from one node to the other, eventually you are able to get a decentralized type of resource management protocol, which we're going to be illustrating shortly. Okay, so that's the idea again. The idea of maximizing the sum log rate. We have all these constraints. Eventually, we got into some particular aspect where we have, instead of solving the achievable rate in general, we render it to be solved in per user. And that's the idea. By utilizing some of those fractional programming, we eventually were able to solve the problem locally per transmitter by utilizing some of those steps that I have highlighted regarding the individual optimization algorithm numerical solution. Okay, so this is the idea. Um, just to highlight or to validate what are the gain eventually that we've got based on that particular framework. We eventually look into some particular extended reality type of system. The first system we looked into is basically a system with 4 base stations and 6 antennas. We have 6 mobile edge computers or 6 UAVs with onboard capabilities. They have 2 antennas each. We're serving across the network 30 users. Of course, these are split equally between strong users and weak users. We have 15 strong and 15 weak users. These are additional type of parameters. Of course, all of them also could be found in the paper I was speaking about. We utilized some of the standard of the channel models for especially those ones dedicated for the XR system that we considered, and we adopted 3 types of benchmarks or baselines. The first one is space division multiple access. The idea here is that we are trying to serve the users jointly, and of course the idea here is we're treating interference as noise. This is the first scheme. Second scheme is we having NOMA. In NOMA, we're still dealing with, in a way, direct links only, no relaying, but we are doing successive interference cancellation. And in our own scheme, which is of course the cooperative NOMA enabled scheme, we have two protocols. One is the centralized resource management protocol, and the distributed resource management protocol, denoted respectively by CRM and DRM. All right. The first set of simulation I'm going to be showing in here is basically about the log rate versus the weak user additional fading in DB. So what's the idea? The idea eventually that we have the cooperative NOMA, as I mentioned, has 2 versions. One of them is centralized, one of them is distributed. The same applies for NOMA. It has both centralized and distributed, and SDMA, it has both centralized and distributed. And the objective that we are maximizing is the log rate. In this particular figure, we're showing that our proposed scheme, in fact, is better than everything. Of course, not just better than everything, but it's acting also as an upper bound envelope in all the schemes. That's simply because cooperative NOMA is generic enough to act as good as NOMA when you have weak user. In a way, we have basically some the weak user additional fading is small enough, in which case you don't really need to do relaying. But when the weak users become weaker, in a sense that the additional fading would become larger, in this case the weak user would no longer enjoying being served by the serving unit, but rather they would rather ask for the help for the strong user, right? And that's exactly why cooperative NOMA here was acting much better than everyone else. Another worthy remark in this particular framework is that the distributed resource management we are proposing is defeating pretty much all the other baseline schemes. Not just that, but it's also defeating them for a negligible loss as compared to its centralized version counterpart. So two important, in a way, takeaway messages here is, of course, first thing is that our proposed algorithm is acting better than everyone else, and also that the distributed management is in fact not bad at all in this framework. It's actually better than NOMA, it's better than SDMA, and it is quite close to its centralized counterpart. Moving forward, another thing here I'm showing is when does Konoma relaying take over really? At which particular aspect of the additional fading, weak user additional fading, the cooperative Noma will be taking over? The idea here is what? Of course, uh, what we have is basically the strong user will when the fading will increase eventually the more strong user, more weak user will start getting served by their own strong users, which is of course truly what we expected. And to best highlight this very fact, what we are plotting here is the low grade versus the weak user additional fading. But here, of course, we are highlighting, we're splitting this objective into two parts. One of them is truly about the strong user, and one of them is about the weak user. What we could see here is truly very, very interesting, is that when the weak user additional fading increases, you could see that the cooperative NOMA, which is this guy, right? It's actually better than everyone else by a big margin. And when what happened to the strong user in this case, you could see that the strong user is in fact sacrificing part of its rate for its own weak user counterpart. That's exactly what's great about cooperative NOMA. As we've seen a couple of slides before, we saw that in fact the sum rate or the low grade, the sum low grade is much better for cooperative NOMA. But we need to look into the details of those. You could see that truly most of this gain of the sum low grade is because we are truly helping the weak user par excellence. Of course, especially when the weak user additional fading becomes too detrimental to deal with. That's why we actually would go into utilizing the cooperative NOMA proposed scheme. All right, that's about what happened usually, especially in the context of XR devices. One strong head-mounted display, another one an actual smartwatch or smart device or a wearable device, which may not have actually excellent link towards the user. So you see that the strong device would try to balance the network by intelligently giving part of its resources to the weak device. All right. The other part is about can Konoma truly aid dense network? And here what we are showing really, we are plotting the low grade on the y-axis versus the number of devices. What we are showing here is that the cooperative NOMA, both the centralized and the distributed ones, in fact, outperform pretty much every single other framework, and that applies both for the underloaded and for the overloaded type of network. In fact, it's particularly in the case of overloaded network where the interference becomes too high. Our proposed cooperative NOMA in the context of XR applications becomes very impactful. Its role becomes more pronounced, and in fact you could see that at some stage the cooperative NOMA, again both the distributed and the resource versions, both the distributed and the distributed versions of it would be in a way outperforming pretty much every other aspect. You could also validate this by checking in fact what happened to the served devices when we have in a way we are trying here to show what's the number of served devices versus the total number of devices. We could see eventually that in fact our proposed scheme, both the distributed and the centralized one, in fact are serving a certain number of users, and by it's particularly validated by the fact that it's actually is going to be doing much better than pretty much every other scheme, because it's balancing the resources properly. When you have some particular weak device, it could be served by the strong user whenever needed, whenever that channel is not good enough, and of course it would still be served by the serving node in case the weak device is in case the weak device has in fact a strong channel. So that's again, it's basically this sort of envelope argument where the cooperative NOMA in fact acts as a generalized norma in many ways, and strictly improved version of it, especially when the link between the weak user and the serving node becomes inferior. All right. So in a way, what we've been speaking about thus far, we spoke about this XR enabled system with cooperative NOMA. We in fact have shown that hey, you know what? We can, by combining the advantages of central cloud and mobile edge computing, but also by adopting the aspects of by adopting the aspects of cooperative NOMA for the sake of improving the link of the weak users, we're able to get very well, especially in terms of the fairness, in terms of the log rate. We've shown when strong users can sacrifice part of their resources to the weak user. We've shown what happened in both underloaded and overloaded type of networks. And of course, we highlighted this very important numerical performance of the distributed implementation because it was working as close as the centralized one. So basically, the idea here is this multi-tier computing is in fact working very well. When you devise the proper centralized protocol, you can actually gain quite a bit, and you can actually get very close to the centralized one without losing as compared to the benchmark. So that's exactly one thing which is very important in next generation future wireless networks, where the proper balancing between the resources and the practicality of the distributed frameworks becomes a very, very important issue, right? So that's exactly what we've shown, the strong distributed joint computation and communication. We showed how we can get optimized sum rate, fairness, and throughput in the practice. Of course, on the other hand, we still would like to know there's issues, especially when you have some online computing heavy optimization required, something we're going to be discussing in the next part of the tutorial. The other part is that yes, what we have devised so far is excellent because we no longer are basing our sort of discussion on single point of failure. Now we have distributed framework, we have cloud, but we also have mobile edge computers. So if anyone would fail, you would have always, in a way, the graceful failure in a sense that we know where exactly to go. We can acknowledge it and we can reroute ourselves to the proper connecting device. Now, of course, we have devised a robust sort of solution to interference, to deployment cases. We particularly illustrated our framework based on some of those XR solutions. We've shown the resilience to blockages, the flexible link selection perspective, especially in the set of simulation I highlighted. But of course, all the simulation results and all the, in a way, the optimization framework we created has been so far based on well-known channel, on perfect channel state information situation. But what happens if we have some channel state information errors? And how can, in fact, we can utilize some of those online data-driven machine learning and artificial intelligence algorithm. So we're going to be considering that. We have already preliminary results regarding this. My colleague is going to be speaking about that in the next part of the tutorial. Before then, we're gonna take right now just a little stop just to see whether you guys have any questions about section 4 on hybrid networks, whether the question is related to the rate splitting and common message decoding part, or the ones related to the extended reality systems with cooperative NOMA. We'll be very happy to take any questions for now. Thank you very much.